I'm going to measure some of the same capacitors I did in my previous video, which will be linked down below. But this time I'm going to use the NanoVNA-F. And the measurements work. A little bit more cumbersome than with the Siglent VNA, but they do work. So the NanoVNA only does linear sweeps. So right now I have it sweeping from 10 kilohertz to 10.1 megahertz, which is a good range for large capacitors. And because it doesn't have a log frequency sweep, you really need to change the frequency range as we test capacitors, as you'll see. But I get results consistent with what I tested before. So let's start out with this 2.2 microfarad capacitor. I'll plug it in the fixture. And there's supplemental charts from the last video, but I'll link those down below too, where you can see the results here. And so you can see here, this is resonating at a fairly low frequency. And so I don't have real good resolution here, but this is getting minus 57.2 dB, and the Siglent got 56.8, so that's close. And if we look up the on the table, that says 34.6 milliohms for the ESR of this capacitor. Now let's take a 0.1 microfarad, like we'll use this one, and I'll plug this one in the fixture now. Okay, so this is a better spot in the sweep range to see. So let's see if I can move the marker down to the minimum. That's pretty good. And this says minus 53.86 dB. And I previously measured minus 53.9. So I could call that this is agreeing with the Siglent VNA. And that comes out to 50.6 milliohms. Now let's take another 0.1 capacitor. There it is, before I plug it in the fixture. Okay. And now let me move the marker down. Oops. Okay. So the NanoVNA has much fewer points, only 101 versus 751 on the Siglent, but it's still not bad. Here, it's still quite usable. And so here I'm getting minus 54.7, and on the previously I got minus 55.5. So off by almost a dB, but it's still okay. And 54.7 is 46.1 milliohms. So I'm looking up on this table, which I'll include a link to. In my previous video, I go into how I derive that table. Now let's look at some smaller capacitors. So let's try this 75 picofarad silver mica. Okay, and it doesn't work in this frequency range. Okay, I already know that this one resonates at about 200 megahertz. So let's change the sweep range on this and do another cal. So we have to go back, go to the stimulus. Let's start at 100 megahertz. Stop at 300 megahertz. I don't remember exactly where this capacitor is, but I'm pretty sure it's in that range. Megahertz. Okay, and now we need to do a recal because we've changed the frequency range. So let's go to cal, turn off the correction, and go to calibrate. And this, the NanoVNA seems to want to do a full cal every time. Partially annoying, but not too bad. So first, let's go with, this is the open. Then we'll use the short, put that on port 1. Now I'm going to use 2 loads and put a load on both ports so I can do both the load cal and the isolation cal quickly. So do the load cal, the isolation cal. And now I will connect up the fixture with nothing in it. And we'll do the through cal. Done. Okay, and now we have a nice cal. So here, so right now the purple line is showing the phase from plus 90 to minus 90. And then if we go back, display, can I tap on this one? No, I can't. Oh wait, I can. I did. And so this is 10 dB per division, and we're looking just at S21. So now let's go back and look at this 75 picofarad silver mica capacitor. And it says minus 37.4 dBm, and I previously got minus 38.2, so it's close. And this one says 172 megahertz. I previously got 173 megahertz. So the NanoVNA is quite capable of doing the capacitor measurements. It's just slightly more cumbersome. If you like this video, please give it a thumbs up. And if you'd like to see more videos from me, please consider subscribing. Thank you very much for watching.